All right. So before getting into the four problems, I'll just take a little bit of more time. So as we discussed that when we write map and reduce, your mapper is run on multiple task nodes, and out of I'll just show you this diagram first. Okay, okay. I think I should just do a little bit of recap on MapReduce because all right, all right. So this diagram should make you clear. So basically, in MapReduce paradigm, or in case of Hadoop MapReduce, what we do is that we write two functions. One is mapper, other is reducer. Mapper is run on each of the nodes where your data is lying. So say you have got a file, huge file, which is spread across 100 computers, and out of these 100 computers, uh, each one is holding a small block of your file, right? Now, whatever code you write in Mapper is run on all of these computers, and the duty of your mapper is to give out key and values. All right. So given any input, how can you convert that input into key value pairs? That is decided by your mapper code. All right. Now whatever is there inside your mapper, which gave out the key value pairs, is your duty. That is the function you write. That's a function declaration you write. And once you have given out key and values, Hadoop will sort it. And after sorting, it will sort by the key, right? Because as part of writing your map function, you write your output in the form of key and values. Okay. And whatever output given by your mapper function is sorted by Hadoop and then grouped by the keys, whatever keys you defined. Because when you give out your output in the form of key and value, so Hadoop knows that the first one is key and second one is value, and it will sort based on the key and then group based on the key. And whatever value that is coming out for each key, there are say 100 values. Those 100 values will be given to your reduce function, which will reduce them, which will aggregate them into a singular value. All right. Now it is completely up to your reduce code what it does with those values for a key. Okay. When I say aggregate, aggregate can be anything what you plan to do in your reduce function. Okay. That gives you enormous flexibility. That gives you enormous flexibility. That gives you enormous flexibility to write any code you want to write any kind of reduce function. Say for example, you want to do something very say out of reduce you can do max, min, or anything you wish. If you want to do summation of is all the square roots of all values divided by total number of values, that can be another form of reduce function. And if you are doing a data research or data science, you would like to apply all those mathematical functions, or you would like to coin your own mathematical functions in order to prepare some numeric value, right? So this, because you are able to write the aggregate function in your programming language, which is whatever you wish, You can form any kind of function even if that is not provided by the system. All right, unlike in databases, when you do group by, the aggregate function summation, average, min, max is provided by the system itself. Okay, only those functions you can use, otherwise you will have to write separate extensible methods. Here it is completely under your control. So the other way to look at MapReduce paradigm is like a group by clause, right? So in a group by, what you do is, given a set of data in the form of tables, you group by on a particular key, which can only be a column. In group by, right, when we say group by this table on this column, and then apply this aggregation function, right? So in group by, we say mark that this is my column, which is a key. Similarly, in while writing your mapper function, you define that this is my key. This key can be any arbitrary, or it can be something from the input which is provided to your mapper function, or this key can be something which you want to create, say reverse of my string, right? It is completely absolutely up to you. All right, now uh, this diagram I would like to walk through you. Before that, Bhupati's question is, executing mappers in all nodes is Hadoop's responsibility? Answer is yes. Okay, so all you do is you write your mapper function, which takes the input, and taking this input, it will convert that input into key value pairs. That's all. You don't have to worry about distributing your logic. You don't have to worry about what will happen in case your mapper is being run 100 times. You don't have to worry any of those parts. All right. All you need to worry about is how is mapper going to convert the input line or input value, the input values into key value pairs. Okay. And in what format, whether I'm going to give record by record to mapper, or whether in we will be giving line by line, that is configurable outside. Okay, so by default, when you pass on, whenever you execute MapReduce function, you do three things. First, you write your map function, and then you write your reduce function. Then you decide on what file are you going to operate. So you give three things to MapReduce: the file on which you want to upload, on which you want to apply your MapReduce, the map function, the reduce function. And then you give all these three things. When I say giving a file to MapReduce, it means I'm telling that this is my file located on HDFS, and run my MapReduce. Okay, as an additional advantage, it basically sends your mappers only to the machines containing your file which you want to operate upon. All right, now you can see that there are two nodes in this example, node 1 and node 2. Node 1 has one section of the file, say example sa, re, sa, ga, and while node 2 has another section of the file. Node 1 takes this input and then runs your mapper function, right? Runs your mapper function. Similarly, node 2 is also doing that. And what is happening in every stage? What is the output? Right? So your mapper converted your string, the input string, into sort of key value pairs, right? Sa is a key, one is a value, and so on. Similarly, in the second stage, this same mappers, these are two instances of your code. Okay, these are two instances of your code, and the second one also converted the input line into sa, re, sa, right? Key value pairs, exactly same code. Now you got two outputs, one on the left hand side, other on the right hand side. Now Hadoop will take both of them and sort them individually. So you get you get as a result of this sorting, you get ga, re, sa, sa, which is sorted list. Similar is in the case of 3. Now, at the fourth stage here, it is merged. Merged as in this list is merged as well as grouped. Okay, here if you see, the ga is only once, and whatever value is there, they are aggregated. This array, this square bracket and comma separated, they represent an array of values, and value here is only 111 every time. All right. Now, so this is after grouping. At the stage 3, you see the data after sorting, then it got grouped, and both of these things, sorting this colored boxes, this whole job is done by Hadoop. All right, it's not done by you. Your duty is writing map and writing reduce. Okay, now what has to be done with these grouped values is decided by reduce, and there you go. So in your reduce function, you have written that just give me the summation, because you do all you wanted to do is word count, and there you get the output. All right. So your map is here is a very simple function. It has just taken in the inside the map, you will see all it has done is splitted the line by space and picked up each word and gave out or spit out the key and value form. That's all it did. And in the reduce, there is another line of code which says sum all the values. Whatever values come as an array, just sum them up. All right. So the input to your reduce function is key followed by array of values, while input to your map function is line by line input or record by record input provided by Hadoop. All right. So I hope everybody is clear here. I'm actually worried a bit about Apurv because he had joined today only. So Apurv, was he able to explain here? No? Okay. Great. So now, Apur, are you with us or okay? So this is the quick recap of MapReduce. Now, most of us think that for MapReduce, you need to write everything in Java, but I mean that was true for in the beginning of Hadoop, but very quickly what people did was people created something called Hadoop streaming jar. Okay, what Hadoop streaming does is it takes an input file as well as mappers. Mappers can be anything in case of Hadoop streaming, and that is the beauty of it. All right, it's a beauty of it that you don't have to, you do not require to code. Okay, you do not need to code. A mapper can be any binary or any command which can give out key value pairs. All right, and the key and the values need to be tab separated, and basically the input which is given to a mapper is plain text file. Yeah, and line by line it is fed to your mapper. Here mapper is my command. Okay, reducer is my command. So how many of you are aware of SED? SED. Yes. So the text file that is given to the mapper is from HDFS. Great. So here, how many of you know about SED? Okay, don't know. All right. So, okay. So the SED basically is a command in Unix which replaces anything with anything, just like your text editor where you say control F and say replace. It's exactly same way. It's a command to convert replace uh, a string with another string in an input, right? Whatever input you give to it, it will replace one string with another. Here, and the syntax is you first SED is command name, and the argument to SED is S slash then your word you want to replace and what do you want to replace it with. That need to be separated by two slashes. All right. So basically this line says substitute space. This is space. Do you see the selection of space? Substitute space with new line. All right. And that's all. So that's all it does. And just as a demo of what it does, so I say echo Sandeep Giri and then I say this. Alright. Now, if I want to replace spaces by dash, so it has replaced in Sandeep Giri. This is the input I have provided to SED by piping it. Alright. Now, this space is replaced by dashes. You see the dashes? Yeah. So that is the duty of a SED, and we want to basically pass this as a command to Hadoop streaming. Okay, as a mapper. All right. Now there is this command, a beautiful command by Unix, which gives you unique list of things. Okay. So if you say echo A and echo A and echo B or echo again B. So a you got it printed A, B, and B. If you pass it, if you pass this input to unique, you only get those values. If you put unique minus C, it gives you counts of each letter in the input, right? Provided the input is sorted. If the input is not sorted, then it gives an error. I'll show you. Echo A, right? Now basically I'm printing A, B, B, A, right? If you pass it to unique minus C, you get strange results. If you see, ideally it could have been two two A's and two B's, but that it did not work that way, right? So unique expects the input to be sorted, and now it will give the correct results. All right. So here there are two Unix commands which are already there on the Unix system. One is called SED, which substitute one string with another, and there is another command called unique minus C, which prints out the counts of unique strings in the input, provided that input is sorted as in ordered. All right. So now what we want to do here is using these two commands. Can we do our word count on Hadoop using these two commands? Using these two nice commands, which are Unix commands. One is for replacing text with another one, and other is finding the unique. So the word count problem, which we had been trying to solve using various mechanisms, now we want to use our existing commands via Hadoop. Okay, we don't want to write any code. We already have these commands which can do lots of wonders for us. So we want to utilize that, right? And in this input file, there is a input folder here. There is a huge text lying, which we want to do a word count on. Okay, so the problem statement is we are given a very huge file and we want to do a word count on that file. Okay, and we do not want to write a single line of code, or we have code in some other form, not in Java, and we want to utilize that. All right, so all we have to do is we have to use a Hadoop streaming library. So the format is Hadoop jar and Hadoop streaming. So Hadoop will run this jar as as a Hadoop job, and this jar is expecting these variables. All right. Now, basically, this command SED command will be run on all the machines parallelly, and once the output of SED comes in, it will be sorted, and after sorting it will be fed to the reducer. And remember, when we talk about a streaming job, in a streaming job, the the output is not grouped. Okay, the output of mapper is not grouped, it is just sorted and given to the reducer. That's all right. Now let's see if we can run it. All right. So any doubt till now, feel free to ask, because I'm not sure that we are all on the same page. Is everything clear till now? Basically, instead of writing code in Java, we are trying to use this library which takes any command as mapper and any command as reducer, and that's all. Right. Amar, Apurv, Bhupati, Rajnikant, Sai, and Sini. Are we on the same page? Okay. The output to the reducer will arrive in different time. No. So all the outputs output to the reducer. Okay, input to the reducer, right? Input to the reducer will arrive at they will arrive at different times, but reducer will only run when all of the input has arrived. Okay, it won't run on half of the results. So say one of the mapper is getting delayed. Okay, so slowest mapper will decide on when the reducer is run, because when all of the mappers finish, their output will be gathered, or will be collected by Hadoop and then merged together to form a single input, and then it runs the reducer. Streaming. Okay, so here there is a misnomer. When we say streaming, it does not mean the data streaming. Okay, it means it's just a little misnomer. It only means that we are streaming the data through our commands. Okay, we are streaming the data through our commands. That's all right. It has nothing to do with that high speed data or anything. All it means is we are running these commands, SED, unique, or anything you want to do. You want to pass your data through these commands. That's why it is called streaming. Okay. Now, mapper and reducer both are basically run as a both are run. Okay. So streaming does not here mean that it is extra fast or it does anything. It is just usual map reduce, where we have got a command for mapper and command for reducer, and both of these commands are run by Hadoop. One on each. The mapper command is run on each chunk, and reducer command is run on uh, you know the aggregated output of aggregated and sorted output of mappers. All right. So when we write Java code, we write our mapper and reducer as functions. Here we are writing our mapper and reducers as separate commands, and we are passing that to Hadoop. All right. The thing is that the mapper gives output in tab separated form, key and value as tab separated, and reducer also expects the values in the form of uh, key and value which are tab separated. And here input to the reducer is not aggregated values, instead it is just the sorted values of all the mappers. All right, is it clear to all of us? If there is a doubt, just stop me and ask. All right, it is very important that you all get your doubts clear, and that is the only reason we have these online live classes. Okay, so I'm just waiting for a minute. If you have questions, just ask me. Even if the question might look stupid to you, still ask it because it would mean a lot. All right. So feel free to ask me a question at this moment. It's very important that we all stay on the same page. So Bhupati, was I able to answer your question? So yeah. So I also to note is that reducer is not run on name node. Reducer is run anywhere. But yes, this I mean this execution of task parallelly is mediated by name node. So name node basically, this is the diagram you're talking about. So yeah, name node makes sure that all the reducers finish, only then the only then reducers are executed. So basically the job tracker name node is here, we should not be calling it name node. Instead we should be calling it the we should be calling it the job tracker. All right. So job tracker creates a job queue, spreads out the job to all the mappers running on all across the cluster, all the mappers running the same code, and whatever results comes, and it will the whole queue will wait until all mappers finish. Once all mappers have finished, then all the output gathered together and mixed and merged, and then reduce function is run. Reduce is run on either of the nodes which are already running the mappers. All right. So whatever reduce is always run on the same nodes generally, because that will at least have little less transfer of data, right? So perfect. So Bhupati is clear. Amar, Apur, Rajnikant, Sai, Sini, Vanaja. Okay. Sini? All right, I think those are okay, great. Now let's try to run it. And so if you remember, let's see, this is our input directory, right? Input this. Let's see what is there. So did you guys try logging in into Hadoop one and try running commands? Do you see this? So we have got one file called big.txt over here, right? So Bhupati, you should try that. Okay, all the instructions are in the session one page, and all of you please finish your quiz first session, that question answers, those multiple choice questions. Please finish those all questions and so that there is not a backlog at all. All right. So make sure there are only some 26 objective type questions. Finish those, and that will help us in evaluating you. Right. Now, here you can see there is a big.txt. Let's see what is there inside it. So to see inside it, either you can say tail. Tail will give you the last 10 lines. Why? Big.txt. So you can see that we have got some data inside it. Now, now let's just try to put it over here and also check whether this output folder exists or not. Hadoop, Hadoop fs minus ls. So basically I'm doing a listing. I'm seeing what is there in my, you can also check it from the browser. If you go to hadoop1.nobigdata.com, there you can type in your login and password, and the login password is again given in the manual on the first sessions course page. Here output 1, output 3, output 4 exists, so we can, I mean, either delete all of those or we can write output 2 because output 2 does not exist over here. Good. Now let us see. So this is our input file. This is our output directory. This is our code, which is mapper, whose duty is which is basically giving us the key and the value. Here value is null because it is converting the input into simply key and nothing, right? So that's all, because it is replacing the space by new line. So each line will have single word, which means there is only key, there is nothing, no value, which is completely acceptable by streaming job. And there we go here. So I'm bringing it to a single line. Let's see if it works. Okay, so it is starting the streaming job now, and it has submitted the task parallelly. And here, since all of the Hadoop is basically designed to be a batch process, that's why it gives you various URL using which you can monitor. Like for example, this one, it's the URL to track your job. It created a job and then gave you a URL to monitor it. There are only total number of 2 maps in total, and they are being run parallelly. So the map process has finished, and now the reduce is running. Yeah. So it says that could not launch, right? probably the unique command which we have given may not be necessary. Okay, let's see what is going on. So we say Hadoop fs minus ls. So whenever it finishes the job, it prints out over here. Now let's see what does it have. It has done some sort of sorting here, if you see. Yeah. Okay, so probably we are looking at the wrong thing. Okay, okay. So this was our job. Okay, it says succeeded. We were looking at the older log. It has succeeded. Yes, it has succeeded finally. It might have failed at a point, but then it recovered. Perfect. Sounds good to you? Right? It did fail here. So as we were talking about, mappers are very resilient. In case it fails on one place, it gives out to another job and then it starts working. Another node. If one mapper fails, it will spawn or create a new mapper on another node and then start working. This is what happened, right? Now it's working fine. All right. So here this is interesting. Now say, do you see this sed command? Here in this sed command, if you take this and do one more, go one more step and say sed substitute, sed substitute any anything anything which is not a to z or capital A to z or 0 to 9. Replace it with nothing. This is what we want to do. Okay, because we see all of these strange characters over here, some question mark, something, and on top of it we want to do a translation. So echo a b c, and we say translate a to z to. All right, this is how you can, using Unix you can convert anything into lowercase. All right, so we also do a translation. So those who are not aware of Unix, do not worry at all. All right, all we are doing is using command line, we are saying convert it into lowercase. So what does this command do? First, it replaces spaces by new line. It is equivalent to saying replace with the space with a new line. Okay, and then we are replacing anything anything which is not, I'll show you this that will give you more comfort. So if you have this, anything which is not English word or which is not alphabet, just replace it with nothing. Okay, so there was in abc dash dash jghj, dash has been deleted by this command, and afterwards we can further do a translation. All right, that's all. And so basically this command helps you cleaning up the input, right? So in this we can go further one step and put this. All right, now your mapper is basically doing multiple things. First, mapper is replacing the space with new line. Once it has done that, it is basically removing anything which is not a single character, which is not alphanumeric, into deleting all the non alphanumerics. All right, and after it has done replacing all of it will trans I will it will convert that input into lower case, so that the casing should not be a problem when we do the word count. All right, now I'm doing the same command again. Let's see what happens. I've never done it before, but let's see what happens. So output 2 already exists. All right, that's not an issue with us. Let's see how what all it does. Okay, all right, and let's see Hadoop 1 and 8000. You can see the HDFS from the web interface also, and this is how you see. You go to your file browser, and there you will see these are your folder. Create your own folder over here before working. So did anybody create their folder? I don't see your folders. No, you haven't created. None of you have created. So, all right. So these are the folders being created. This is where we stored our previous step data. Okay. Let me see. Amar is saying that Amar has created, and okay, you must have created in the, all right. So I say SSH. Okay. So Bhupati's question is that can we have two mapper functions? Output of one mapper is input to another mapper function. So the idea is that if you are making two mapper functions as two separate processes, why don't you merge them and make a single one, right? But because you anyway want them to run on the same node, right? The output of one being passed to another one. But it is entirely possible to chain mapper and reducer one after another. Okay, the output of one set of mapper reducer is given to another set of mapper reducers, and that is entirely possible. Okay, but I mean, having two mapper functions piping the input from one to another is okay as long as it's inside the same command, the way I have done here. If you see here, I'm piping the input of replacing space with new line to translation into lowercase, and then I'm piping that input to translating to sorry, here these are three processes running one by one. That's completely possible. Let's see if we got an error or something. Yeah, we got error over here. What does it say? Okay, okay. Attempted sub-process failed, and it says the piped is not working. Okay, sub-process failed with the code 2, and job is not successful. Okay, job is not successful. Let's see further detailed message here. This is the URL to track the job. Yeah, it says there were two started attempted maps, were 7 attempts were there, all of them were failed, and 0 was successful. So 1 was killed, 7 failed, and the error was sub process failed with code 2. And okay, okay, This is okay. Now see the logs. So it says cannot read this. Okay, we were actually trying a wrong thing. Let's see what we have done. Okay, looks like we cannot pipe the output like this. Instead, what we can do is we can actually, okay, okay. All right, so here we can write my cmd.sh. So bin bash. So basically right now the problem is this Python streaming is not accepting our command as is. So what instead we will do is we have taken all of these three commands and put it in my cmd.sh. Okay, and we will have to ship it. There is a in Hadoop streaming. I have it in the next session. So there is a possibility of shipping it together. Okay, don't worry. Now we have Hadoop streaming and streaming ship. Okay, here this is my file which we can write like this. All right. So I've just written my script, my command.sh. So all the things which I wanted to do in pipeline, A, pipe B, because in Unix you can create these beautiful pipelines. And I was trying to do that. Okay, output folder exists. That's a nice error to have. And we can say output 6. I think 6, right? Let's see my sgiri. Where is my folder? This is my folder. And under that we have word count. So output 5 we have. Then we can have output 6. Output 6. Now let's see what happens. Okay, so what I did just now is, since I had a lot of work to do, I have three jobs. First was replace space with the new line. Second was replace anything which is not alphanumeric with delete, I mean don't, I mean replace it with nothing. And then third thing which I wanted to do in the mapper was translate to lowercase. Okay, convert the input into lowercase so that the keys are grouped properly, the words are grouped properly. So let's see what happens now. Because streaming job was not accepting my job as a piped one, I have put it into a separate file altogether, and then see what all errors do we get over here. Okay, now let's see the, it must have given us one connecting this. Here is the URL to track. So here I'm trying to show you that how do you debug your Hadoop job. So whatever job URL it giving, the URL to track the job, open that URL, right, and go into it. What is going on inside it you'll get. So it's saying that again it's same thing happened. There were 7 failed attempt, 1 killed. Okay, and what exactly failed over here? Let's just pick up the first one's log. Okay, let's see what happens. It says, okay, yeah, Hadoop yarn, this is my command. Okay, it says there is no such file or directory. Why does it say that? Okay. Looks like, so we can't we just say, this is correct, right? This is correct. And I forgot to remove single quotes. Good. So if you put single quote around it, it will consider the whole thing as a single command, and probably that is the reason why it is giving error. All right, good. Output 6 exists. Don't worry. Now we'll change it to output 7. Is everybody following, or have I lost you? Okay. So Rajnikant is saying that SED command is, yeah, SED command actually works on Unix only, and you can, you if you want to use these commands on Windows, what you can do is you can use Cygwin. I have used Cygwin whenever I have. Cygwin is basically a port of all the Unix commands onto Windows, and it works beautifully. Lots of automation you can do using Cygwin. And okay, Bhupati, let me just. So Bhupati is saying he's lost. Okay, let me try to bring him back. So up to here you are clear, right? Here, up to here, right? Rajnikant, try increasing the volume at your machine. Probably that is the thing. Okay. Is my volume really low to other people also? Okay. Okay. So, Bhupati, let me try to explain to you again. So, instead of writing, mapper like this, okay, here we were writing the command directly, and we wanted, as you said, that you wanted to pipeline the input from one to another, right? So we wanted multiple commands to be executed as part of mapper, right? So instead of, and this one was not accepting all of them as a piped commands, right? In Unix, you can pipe the output of one process into another by putting a putting a character like this, A pipe B. So whatever output which you get out of A will go into the process called B, right? The exactly the way I have shown in this line. Now this one, you see, there is a echo S and D. What it did was, I'll show you this. So I step by step. So what it did, it replaced space with a new line, right? And now whatever is the output here, the next step is whatever output came into place, we are replacing it with replacing a non-alphanumeric. So let me just put something else. So here. right? So I'll go step by step. That will look really nice to you. So you have got these two words, S plus and D, or you can say, and here you have got capital S and capital D, right? So this is your input. This was your input line. You replace the space with a new line. Now the next step is you remove, sanitize, you sanitize anything which is non-alphanumeric. This is the command. So for time being, you can assume that this command exists. Basically, we are replacing anything which is not alphanumeric with the nothing. So if you see, plus has been removed. This S plus has been converted into S. Now the next step is to convert everything into lowercase. Okay. Next step is to convert it into a lowercase. All right. So here you can see that everything has been converted into lowercase and very well sanitized. All right. Now let's see if we have got some output, right? So all this command, all these three things together, we have put in a single file. All these three command, this command, first SCD, second SCD, and then third TR, we have put in a file, in our file, and passed it to the streaming job, right? Now streaming job did its duty and did the job. So this is the command we ran. Now whenever you are writing your own script, this my command.sh, which I wrote as a script in which there were three commands written inside it, I basically passed a argument called minus file, which means that this file, which is located locally and not on HDFS or not known to all the nodes, is also shipped to all the nodes parallelly. Okay, it shipped it to all the nodes parallelly, and we got our output in Hadoop as Giri word count and output 7. Not this, let me just say fs minus ls. All right, now we have part, and if you see there should be something inside that one, and let's see what is there. All right, so there are numerals. All right, so basically it converted everything into a clean format. Words are only left like this, and if you want to see that what are the top 10 words, and it should give you. Now see, the is the one which has come 80,000 times. All right, and some tab character or something. So there is some invisible character over here. I don't know what is this. I have to look into this clearly to understand. Off has come these many times, and has come these many times, right? Space, but we replaced space with new line. So I'm just wondering what is this, right? So this is the general frequency of the words which has occurred in this file, right? And if we can say 100, these are the top 100 keywords. Right now, the output of reducer is not sorted by frequency, right? So you can see. So in English language, the most used word is the, and it's also most redundant word in lots of cases. And then of and to and in, then a, he is more frequent in this particular file as compared to she, but her is more frequent than him. This is interesting. Awesome. So we were able to successfully and cleanly run our run our streaming job. And I also, as part of this demonstration, we did couple of things. Okay, first we tried to run a Python all Unix command as Python 1, sorry, all Unix commands as streaming jobs, right? And also we demonstrated that any command, any script you want to create as a mapper, you can write it as your own script. And by going for minus file, it is possible to hand it over as a command, right? Now, I mean, if you have lots of commands as mapper, or you have a script, or you have a Python script, you have a binary, you have C++ class, C++ task, or you have say any other programming language you can think of, you can write it as as a shell command and give it to Hadoop, and it will execute happily. Okay, any command, completely any command, as long as, if you're passing it as a mapper, as long as it gives appropriate key values, and in a reducer, as long as it does its job, any command which you can run from the command line can be handed over to Hadoop. Even if it's your own script, you can ship it to all the nodes. Now let me try to answer Bhupati's question. Let's say I have 3 data nodes and the file I stored is 100 GB. So name node will divide 100 GB between these data node 60 MB chunk, and while running this map reduce, this will do operations in memory. Um, okay, so name node has finished its job by creating 64 MB chunks, and since you have only 3 data nodes, which means how many chunks are going to be there? Can somebody give me? In our case, in our installation, the chunk size is 128 MB. Okay, or let's say in your case 100 GB. 100 GB is this much MB divided by 64. So in total 1600 chunks are going to be there, or 1600 blocks are going to be there in those 3 nodes. Okay, if you have a replication factor of 3, then there are going to be these many blocks in total. 1600 into 3, which is 4800, and those, each data node will have 1600 blocks located and making it 4800. All right, now, so name node will divide 100 GB into these 3 data nodes. Okay, while running this map reduce, will it do the operation in memory? No, it will read each chunk, each 64 MB chunk, and then run your mapper against it, and whatever output of the mapper comes in, it will keep on writing into the disk. And once it has done finished the job of all the mappers, then it will sort it locally, and then it will let it merge. Okay, great, great, great set of question. And Perfect. So we were successfully able to clean up our input using these very simple commands and create a nice frequency, create a nice frequency graph here, frequency chart, if you see, right? Now, sounds good to you? So those of you who are not comfortable with Java, you can use streaming job. The other reason to use streaming job may be the way I am far more comfortable in streaming jobs because you don't have to code too much. If you are handy with command line Unix, you can quickly get your job done by writing shell commands and passing it to streaming. Instead of if I had to do the same thing which I just did, it will take me quite some time to write that code in Java. Even though I am fairly confident about my Java skills, still writing code in Java or any other compiled language takes a lot of time as compared to do it in scripting. Okay. Also, Unix has got great, like for example, we said tr, which is translates to the lower character, which is quite simple in our Java code. Also, we say xyz dot to lower, right? Similarly, if we have, but if we had to replace it, if we had to replace it, we will have to use again the regex, and you'll have to write classes, and it will take a lot of time when you, as compared to writing it in command shell script, it takes a lot of time using Java, right? Therefore, there are two reasons to use Hadoop streaming. First, first you may not know Java to do the map reduce. Second, Java writing code in Java takes time because you have to compile, bundle, ship, upload here and there, and then and the third reason to use Hadoop streaming is if you have a legacy code. Okay, you have a legacy binary code which runs, which works fine, but you have got legacy code which runs absolutely fine, but you want to run your data through a legacy code. Now you cannot translate this legacy code into Java. You have to live with it. So you can pass your legacy code, legacy binary to streaming, and it will do the job for you. Okay, that is third reason for using the streaming job. Perfect. Should we move on? Right? This we have explained earlier that this is what happens. Alright? Now hands-on is finished. Good. Perfect. So here we are. Okay. Okay. Now anybody? So these were the four questions which we talked yesterday. Just now, as I demonstrated, that this is how you do the word count word count exercise, right? You took a word count and it did made that as a key, and Hadoop counted it for you. So if you had to count the frequencies of letters A to Z, if you had to count the frequencies of letter, do you still need to use MapReduce? Anybody? Did anybody attempt it? If the file is spread across data nodes, it is easy to map reduce, if not just good. Good. So Sai is saying that map reduce is not required. To some extent, yes, he's right. The thing is that if you see that at the end of day you only requires 26 variables, right? Or integers, 26 integers, count of a, count of b, count of c, and up to count of z. So we basically require 28 numbers in memory, right? Can we find a way better than MapReduce? If you think about it, if each block, if you convert into key value where key is a alphabet and value is number, then basically there are too many values for a key, right? There are too many values for a key. So if you think that you have got 10 GB file or say 26 GB file, and you assume that all the character frequencies are equal, then the size of the value is going to be 1 GB, right? For each one. So if you have 26 GB input and we assume that at least one letter is going to have more than 1 GB values, right? So does it make sense still to do the computation of frequency of letters using MapReduce? Computing frequency of words was fine, but does letters make sense? So yes, so basically what Bhupati is saying is also right. If you have a file which is spread across the network, then let all those nodes do the counting for you and then you can aggregate. All right? Right? So so in this case, CPU will be the bottleneck, and when you are reading the file, and if this file is spread across network, reading from the network might take more time. Instead of transferring these 26 numbers from one machine to another, if you transfer the file, that will take more time. Therefore, spreading out the computation to the whole cluster is very important, right? So that's so even though the RAM is not a limitation in this particular problem, I mean, but CPU and the network will become a problem, and the read speed of the disk, if everything is located locally, will become the bottleneck, and therefore distributing the computing to across the cluster is helpful. All right, but you'll have to do a little bit more of uh, you know uh, merging. We will talk about how do you summarize the output of mapper on the same node before getting transmitted to another node. Okay, we'll talk about that aspect in the next session. So all right, so this was the first problem. Second problem, right? Right. So this is an example, a walkthrough of how would you do the map reduce. So mapper one will give the frequencies of letters up to A to Z. Similarly, mapper two will give its of frequencies of letters, and then after that reducer sums up at the end. Okay. Now that was straightforward, right? Because each mapper will give out these numbers and then you sum it up. Now the next problem is little tricky one. Next problem is little tricky one. Now you have to find anagrams. How can you find anagrams using MapReduce? What is anagram? Anagram is a twisted letters, I mean rearrangement of the letters of a word. So cat, tack, and act are all anagrams of the same word, right? So in the same fashion, if you have words like tar is art and rat and so on, right? And so on. These are all anagrams. Now, how would you write MapReduce to compute the anagrams? Out of the okay, do we have any calculation on number of name nodes and data nodes, or I can have one name node? So you can only have one name node at a time, and you can have many data nodes, and it is up to your hardware capacity. You can have as many data nodes as you want. Okay, upper limit is quite big in terms of numbers. I mean, upper limit is in few lakhs on number of data nodes. It's completely up to you. It's up to your the amount of money you have in the pocket. Uh, right now, anyone? You have to find anagrams in huge text. You've got a huge text file, word by word, and you have to find anagrams in that. What will you do? Uh, uh, uh. Oh, actually, I'm not able to see any of Apur's questions. Apur's has been posting questions. Probably he's using the web view, and that may be one of the reasons. I don't know, but I'm not able to see any of the questions. Strange. This is strange. Okay. So anybody with respect to this, I'm actually waiting for your answers. Read the text line by line with words and compare the words characters and the same. So reading the text is not up to you. You cannot freely read text. The Hadoop will read a line and give it to your mapper, right? Now using so you have to form a key such that you have to form a key such that all anagrams have the same key, right? Because if you are able to form a key such that all anagrams of the word come together, because Hadoop will be grouping it for you, right? If that happens, then it's quite simple for you. Group by same length words and shuffle words between them. Okay, okay. So basically, the task is to prepare key for each word such that that key should be such that all the anagrams of that word will have the same key. What could be such key? Group by same length word and shuffle words between them. So Bhupati's point is that if you have the same length and then shuffle words between them, but there could be many words which have the same length, right? If you form the key based on the length of the word, then you'll have lot of words. But this is a good approach. Lot of words, you'll have lot of words for the same length, and now you have to find out between these words. Although you have decreased your subset, but still, say for example, size 3, right? Size 3, there will be lot of words with size 3. Okay, practically there could be 26 to the power 20, 26 to the power 3, right, for a set of 3 letters. So and similar is for other words, so you'll have to do a lot of churning again. And Amar's point is that anagram words with the same key to referring. So if you can figure out a key for a word, key as in when your mapper should give out the key and the value as the word, and the key is something which should be common for all the anagrams of this word. Okay, what is that key? How should we create that word or some sort of symbol which basically should be same for cat, tech and act? Okay, all of them have same length, same characters. So can we do something like let's say say we sum up the values of these characters A, C and T, right? So will it form a number which will be equal in all three cases, or right? Or there could be a very very simple thing, but if you see, if we sum it up, so CAT cat would be equal to, thus if you sum it up, it will be also equal to CBS, right? CAT, if you sum the values of each character, will be equal to uh, CBS, right? Sorry, not, I was supposed to send it to entire audience. All right, now we can't do that, so we'll have to come up with some other nice idea such that all the the all the words produce the same key if they are anagrams, right? So one is that there could be multiple. We tried doing a sum of all the words. There could be other things, right? Such as we designate one prime number to each letter and then multiply those prime numbers, right? That will result in the same value. But that is little too much to do. A very simple one is the sort the letters of a word. Okay. sort the letters of a word, right? So cat will, the if you sort the letters of a word cat, the it will be ACT, right? And same is if you sort the letter of tech, it will be ACT, right? If you sort the letters of ACT, it will be ACT, right? So all of them, all of the words, if you sort their letters, are going to produce the same key if they are anagram. All the anagrams are going to produce the same key. If I mean same if you sort their letters, right? If your key is based on sorting the letters of a word, then all the anagrams are going to produce the same key. Does it make sense to you? Bhupati, Sai, Apurv, Rajnikant, Sini, Rajnikant, are you with me? Okay. So basically, as we talked earlier, we have to run the mapper. Basically, our mapper will have to give out key values, right? And then Hadoop will bring all the keys together. Okay. The keys which are identical, it will group them together, group the values together, right? That is the duty of the mapper. So here our job is to find out the anagrams, right? And hence we want to bring the all the anagrams together. And the only way to bring it together is to form a key out of the word such that all the words whose anagram need to be computed, who are anagrams, they produce the same key, right? So you sort the letters of a word, right? You rearrange the letters of a word such that A comes before B comes before C, and so on. So that is sorting the word in itself. So here, if you see the cat act in tic-tac-toe, the mapper is sorting the letters of a word. So for the, if you rearrange the letters in increasing order, you will end up with EHT, right? EHT is the key and the is the word, right? Same is the case with with cat. For cat, if you rearrange the letters, it will become act, right? And cat. In case of act, the word will remain as is, act. In case of in, the word will also remain as is. But in case of tick, right? So the key is sorted characters of a word, and the value is the word itself, right? Rajnikant, are you with me? Good, good. So now here, same is the case with toe. In case of toe, if you see, we have rearranged the letters. Now key is that rearranged value, rearrangement of the letters such that they are in increasing order, and the value is in this. Now you can see very clearly, cat, act, and tech, all of these words have the same identical key. All three of them have act as the key, right? Now, since the keys are being sorted and then grouped together, now they have come together, you see. And reducer will do nothing in this case. It will just remove the other words. That's all. All right. reducer will not do anything at all. Does it make sense to you guys? Great, great. So we solved a very, very important problem here. It's a difficult problem to attempt in first shot, but the overall trick in forming MapReduce is to basically figure out the keys. Figure out the keys. How do you do the key? Figure. I mean, what keys should be the should be for your record? Okay, right? All right. So let's take a break for some time, and we come back after 10 minutes. Okay. Let's take a quick break. Let's come back at let's take a break for let's come back at 8:50 in 30 minutes. Okay, not 30 minutes, in 13 minutes, 1 3. All right, great. See you in 13. Hello. Hi, Virdi. Welcome back to the session. So far we have been discussing the problems which we gave last time. This was the anagram problem which we just discussed, and we are actually in the middle of break. And actually, I'm back. In case you guys are back, we can start. Actually, you missed a very important part. We demonstrated how can you, without writing program, how can you use shell script or any command as mapper, and how can you use any command as reducer. This would have been really interesting for you, because the kind of problems, as we discussed earlier, the kind of problems you are planning to solve using Hadoop is basically are in legacy code. Okay, so are you done, or with the party, or you are going to join back? Okay, okay, great, great. So basically, the kind of things you are planning to do with Hadoop is basically you have a lot of legacy code and you want to run that through Hadoop. So for that kind of job, that kind of task, it's very interesting to have that I mean, to run all of this it through something called Hadoop streaming. All right. But don't worry, you will get more better ideas. And even if you are not understanding the map reduce right now, do not panic. Do not panic, because you will catch up. No worries. Okay. And so, did you try to attempt the anagram problem? What was your solution to anagram? How do you find anagrams in the big text? Yes, yes. Go ahead. All right. So, is everybody back? So, should we start now? Great, great. Great. So in case of anagrams, we had to find the same key for all anagrams. So all we did was we formed the key by sorting the characters of the word, and for all the anagrams, the result will be identical, right? Now let's move on to next set of problem. The next set of problem is quite simple. Third A. You are given the DNA sequence of all the people and find the people who have the same DNAs. Anyone? So we have the input like user 1 ACGT and user 2. Here user 1 and user 4 have got identical DNA, so we have to find out user 1 and user 4. And user 2 does not have another buddy who has the same DNA. So yes, please answer the question. So you are given a big file containing the DNA sequences of people in this format. So the name of the person, which is user 1 here, and then followed by a DNA. You have to find you have to find all the people, you have to group all those people having the same DNA. What should we be doing? What should be the key? Extremely simple question. Same as anagrams, but why? In case of anagrams, we had to sort the letters, right? Here, we are talking about these two persons who has exactly identical DNA, right? Not twisted one. It's the same identical one, right? So people who are with exactly identical DNA, we have to group them together. Like this person and this person, they're identical, and we need to group them together. Key should be DNA. Very right. If we have key as DNA, and then yeah, sort by values at group, right? Sai, that's the point. So if you have to sort by values, you have to make that value as the key, right? Because Hadoop only sorts the keys, not the values. Right, right. So DNA as the group, as the key for sorting, which is done by Hadoop, and then let Hadoop do the grouping for you, and you just in the reduce you do not do any special work. All right. So I hope that this is clear to all. Here, your creativity as part of writing maps reduces. If you are writing maps, your creativity involves in figuring out what should be the key, which is the output of your map function. So if you are writing a map function, your creativity will be to figure out what should be the key. And that should be the premise of solving almost all the problems, that in a mapper, what should be the key such that you are able to solve your problems. Okay. So this is quite clear to all of us. Now let me just take it to another level. Okay. Now the next point. You figured out, now you have to group all those people together whose DNAs are either identical or exactly reverse of each other, right? So user 1, user 2, user 4, they all have either identical or exactly reverse. So user 1 and user 2 has the exactly identical reverse DNA of that of user 1. User 1's DNA is ACGT, while user 2 is exactly opposite, like TGCA, right? Now you have to group these users together who have either exactly opposite DNA or exactly same DNA. How would you do that? So is problem statement clear? What should your map function do to make the keys such that all these people with same DNA or exactly opposite DNA should, or reverse DNA should come together? How would you find out such people whose DNA is either same or exact reverse, or I mean that way, right? So how do you solve this problem? Anyone? Okay, okay. So here is the problem. Basically, you are given the same file as in the previous example. In the previous example, we grouped the users which have identical DNA together, right? User 1 and user 4 in this case. Now in this third B problem, we say that please group the users which have either identical DNA sequence or exact opposite of each other, right? Mirror image of each other. So user 1 and user 2 belong together because AGCT is exact mirror image of TGCA. TGCA. If you reverse the string, you will get the user 2's DNA, right? And user 4 is exactly identical to user 1. So user 1, user 2 and user 4 belong together. Is it clear now, Vidhi? Okay, so Vidhi's attempt is use anagram logic on DNA with the mirror image for sorting. Okay, okay. So what you are saying is that do the mirror image for both. But if you do the mirror image, then user one's key will become TGCA, user two's key will become uh, ACCT, and user four's key will become TGCA. Now user one and user four will group, but user two will not come in that group, right? Ideally, user one, user two, and user four should group together. Oh, okay, okay. You got it right. You got it right. Good, good. So either of mirror image or same image should sort together. So if I understand correctly, you are saying that whether mirror image, whosoever is smaller of the two, mirror image or itself, should be the key, right? If you sort them, or maybe if you order them, it will form an array and you can keep that as a key, right? So either of that. Good, good. Any other ideas? Bhupati, are you with us? Sai, Rajnikant, Sini, Apurv, Amar. So what is your attempt to solving this problem of finding people who belong to the same DNA family? Okay. Reverse the DNA. Okay. The key should be the reverse of DNA. Is that what you're saying? Amar's point is DNA is the key for all the persons. For mirror, we need to take array and letters reading from last from the array. Okay. Okay. You have got a point. So Amar is saying that take the DNA. Okay. Okay. No, actually I did not get it. So I was thinking that you are trying to form the array of the word and its or of the DNA and its reverse. So there will be an array of two entities. One is DNA itself and other is reverse of DNA. And if you sort these two words, then the key should be same, right? For all. That was, I think, Virdi was also having the same answer, right? If you have, good, good. So should we move on, Bhupati? And okay, okay. So, all right. If you have questions, just stop me, and I'll love to answer the question. Even if you did not get the problem, I'll like to explain it again. So, yeah. So the trick here is to form the key where these two users will come together, user 1 and user 2 and user 4, and that is only possible if you take the smaller of the DNA and its reverse. So whatever it is, say TGCA and ACGT, who is smaller out of these two words? Quick, who is smaller, ACGT and TGCA with respect to ASCII values? ACGT, perfect, right? With respect to ASCII value, if you order them, A will come before T, right? So ACGT is smaller out of these two. So if you reverse a word like ACG is there, if you reverse it, GCA will become out of GCA and ACG, who is smaller? ACG, right? And in case somebody was having GCA, now let's take this and put it in a text file so that I can clearly explain. Now we have got this input, right? Now for this one, what we do is, what is the reverse of ACGT? Quick, what's the reverse? TGCA, perfect. Now out of ACGT and the reverse TGCA, which one is minimum? Smaller of the two? ACGT, perfect. Now let's pick up the another one. Now reverse of TGCA is ACGT, right? And now minimum of TGCA and ACGT is, what is the minimum of the two? ACGT, perfect. So we notice that when we do this, here TGCA also results in ACGT and ACGT is also resulting in ACGT. So this is a good key to have. Now, so this sounds like a good idea, right? Now this is what will happen. So if you keep the smaller of DNA or its reverse as the key, these are the keys that will be formed. Does anybody has a doubt about it? So first one, user one will become, the key will become ACGT and user one. For second one, the key will become ACGT, the way we explained here, the way we explained in this, why the key for the second one is ACGT. It's a smaller of the DNA itself and its reverse, right? And the smaller is ACGT. In the third case, ACG and user 3 and ACGT becomes as is, and so on, right? So the whole idea is, with how do you solve such kind of problems using MapReduce paradigm, and we are able to break down the problem of finding DNA and its reverse is into a sorting problem. We are able to figure out the key on which the data need to be sorted in order to solve our problem. And the key is formed by finding smaller of the DNA and the reverse of it, right? So now the rest of the game is pretty obvious and simple. Now Hadoop will take this line shows that Hadoop has taken your input and sorted by the key and then grouped the values for the same key, right? User 3 and user 5. And reducer doesn't do anything per se. All right. So is this clear? Should we move on to the next problem? Okay. All right. Now this is done. Moving on. Now this is little tricky problem. This is little tricky problem. And in the case where you are trying to solve a bigger problem, you will have to figure out how do you solve these problems. But it is important to understand. It is important to understand these problems because if you understand this problem, you will understand why Pig Latin has the syntax the way it is. For example, when you join tables using Pig Latin, Piglatin is something which does MapReduce under the hood. You do not have to write these mappers and reducers. All you have to write is the query language of Piglatin, right? Now, when you do joins in Piglatin, you cannot join two tables the way you used to join earlier based on where A is greater than B plus 13. That kind of joins are not possible. Joins are only possible on top of keys, right? So similarly, I mean, for understanding why that happens, it is important to understand how would you do a join using MapReduce. And this problem, the fourth problem, basically explores the joins of two big files, right? So who all know about joins in SQL? What does it mean by a join in SQL? Okay, Virdi does. Great, great. So probably all of you know the SQL joins, perfect. Now, this problem actually explores how do you do the joins using MapReduce. Okay, although you will not never have to do the join by yourself using MapReduce, because you will be either using Hive or Pig, who will translate under the hood into what we are going to do right away. All right, but it is very important to understand what goes beneath the skin of Pigletin or Hive, that you can understand by actually trying to solve this problem. So in this unusual democracy, the votes are measured in terms of how rich the voter is. In case a richer voter is voting for you, you get more votes. In case the poor voter is voting for you, your vote count is less, right? So there are two lists. List 1 contains voter and votee, meaning who voted for who. And list 2 contains people and the worth, right? Now your objective is to find out the sum of all the people who voted for various people. Okay, find out the sum of all the worths of people who voted for a person, and you have to do it for all the persons who have been voted. How would you do it? In SQL it's quite simple. You just join these two tables and then do the sum, right? You join it, group by it, and then sum it up. That's all you need to do in case of SQL. Now how do you do it using MapReduce? Anybody? Okay, okay. So we'll go slowly, one step at a time. Yes, replace voter with the worth and votee as the key. This is what we need to do. All right. Now, now let's see what we can do. So what we did, first of all, we are given two files, list 1 and list 2. List 1 contains voter, votee, and person and its worth. All we did was, as a simple task, we just merged them together. We just concatenating these two files one after another. All right, that's all. That's all. So Mapper did not do much. It just concatenated these two files into one. That's all. Right? You put both of these files together in a folder and you supply it to the mapper. They are by default concatenated in itself. Now, as part of reduce, you will get these values. Okay. As part of reduce, you will get these values. And reduce also did not do much. But again, there is another chain of mapper is run on this particular single file. What this mapper did, so Hadoop sorted it, grouped it, and mapper just kept it as a comma separated values. So here, if you see, a this is voter votee and you concatenated this. So AC, AB, BC, CF, and then A5, B1, C1, D1, they came into picture, right? Now, when Hadoop sorts them, all the values of A will come together, like 5 comma B comma C will be the values for A as a key, and so on, right? Now, what you got at the end of day is this table basically says that A, whose value is 5, has voted for B and C, right? B, whose value is 1, has voted for C only. C, whose value is 11 and has voted for F only. D, whose value is 12, has voted for nobody. Okay. Now you write a second phase of mappers. Bhupati, you remember you asked me how do you chain the mappers? You do chain the mappers in like this. So mapper, reducer. Reducer can go missing, and I mean reducer may not exist for a process. Okay. Now mapper 2, what does the second mapper did? All it took key and values, each key and values it read, and it printed like this. For all the values, it printed B5, C5, and so on, right? For each value, like this first line, it printed these three values, right? B5, C5, A0. Similarly, for this one, it printed B0, sorry, here C1 and B0. Okay. Now if you see here, it says this table says A voted for B and C and A's worth is 5, right? And after this stays here, it says that these are my worths. So the worth of B, because of the first line, is 5. Worth of C, because of the first line voted by A, is 5. And because A voted for these people, A's value is 0. A did not get any value out of it per se, right? I'm putting A as 0 because I want to display 0 against a person who has not been voted at all. Okay. Otherwise we do not need to display the people who got 0 as the end of it. Similarly, by virtue of the second statement, C got a value of 1 while B we had just printed as 0, just for the sake of it. Now this table is the result of this table basically says what is the values of various people. If you sum up the values of each one here, you get the overall values, right? So if you sort and sum it, you'll get the values. So for A is 0, for B 0 comma 5, for C 5 comma 1 comma 0, for D is 0, and F is 11. And if you sum up these values for each one, you get their total worth because of the voting. Does it make sense? No? All right. All right. Perfect. Perfect. So we were able to do a complex problem using we were able to join two tables. First we joined these two tables, then we did a group by and we got the value. Okay, right? So this is how, just based on a simple paradigm of key values, you could do join, you could do group by, you could do filter in future, and you could do almost everything, right? Had it been a clause in voting that if a person's worth is greater than 10, ignore them, right? Had it been that the case, then in this mapper you will filter out the values here itself so that you do not list C and D. So you can do where clause also. This is an example of where clause what I'm talking. So here we talked about really interesting problems, four different kind of problems, where anagram kind of problems are difficult to solve. Here, anagram or DNA, the part B of DNA, is difficult to solve using traditional SQL, even with syntax wise, because reversing a string takes a lot of effort in SQL. And there could be other difficult operations like comparing the keys and all those things that could become a difficult challenge when you deal with SQL, right? But that's quite simple using MapReduce. So for certain problems, if you are not able to solve it using pig, you might have to come back and solve it using pure MapReduce. All right. Now, what are the limitations? We talked about MapReduce so far, and we have started thinking that the MapReduce is probably the answer to all our problems. Now, what are the problems which MapReduce cannot really solve? And you should avoid using that, using MapReduce. Okay. First, if the job can be done using a single machine, do it using single machine. Do not go over to MapReduce. It's as simple as that. Okay. If you do not have a graph, I mean, if you do not have the future plans where the load might become bigger, then there is no point in using multiple machines. Okay. And while do you do the planning for this kind of thing, that in future whether your data grows big or smaller, will I be able to handle? The simple back of the envelope calculation will really help you. You should understand that what is the relation between the size of the data and number of comparisons which are going to happen inside. If you are able to figure out that relation, that for 5 records I need to compare 5 times, for 10 records I have to compare 25 times, right? If for say for further, if we keep on growing this way, okay, so there should be a clear, there should be a clear correlation between your data and the time taken by the result. And if you have that clarity on your processing as well as the rate at which your data is growing, then you can take this call reasonably easily. Okay. The way we did our first exercise where our sorting was taking 5 hours, you should try to figure out the relation between your input data and time taken first. Second, you should try to figure out the user requirement, where you should know that for after how long how much data is going to get accumulated, right? So if after doing your back of the envelope calculation and doing a little bit of analysis, you realize your data is smaller, it is going to be smaller, and your churning can happen fairly easily on a decent size computer, then you should do it on that computer. You should not just to take the benefit of MapReduce paradigm itself, you should not be writing the MapReduce, because MapReduce is not a programming, something which helps you in coding. MapReduce is something which helps you in the performance. MapReduce is something which helps you solving big data problems. Okay. Unlike in the earlier times, we had a map and reduce construct in the programming language itself. Perl has its own map and reduce concept. So it's not that way. Okay. It's specifically used only if the data is bigger, because if you start using map reduce for even a smaller data, the performance is going to be really awful, and you'll say this map reduce is worthless. Okay. Computation depends. Whenever we saw that in MapReduce, each map runs on independent set of data. It does not depend on another MapReduce data, right? In case your computation depends on previously computed values, you cannot use MapReduce so easily. It becomes really, really impossible to solve. Okay. So for example, if you have to compute the Fibonacci series, then it's not possible to use MapReduce. All right. Text indexing and ad hoc searching are bad examples of using MapReduce, Apache MapReduce, Hadoop. And fourth point is, if your algorithm needs a central cache, say you are running multiple MapReduces or multiple processes which are updating a central cache, and your program need to access this central cache all the time, then you are doomed, because on each execution of map it is going to hit your cache, and your cache may not handle it, as well as it will totally slow down your system. Therefore it is strongly avoided. In case your algorithm is depending on a global state, then it is strongly avoided for MapReduce. Is this like a fourth problem? I did not get that point. Which one, Bhupati? I lost the context. Okay. The second point, computation. Not really. Computation here in our example of the fourth one here did not really depend on anything. We were fairly independent. Okay. But here, like Fibonacci, not really, not really. Here, if you say, we are actually dependent on the whole data rather than previously computed. Say if our say this whole data is being divided parallelly onto hundreds of computers, right? And say one of the maps requires the computation of first five lines before the next five lines can be computed, right? Then it becomes impossible to use that. So when I say computation depends on previous computed value, means first 10 records only when the first 10 records are going to compute, then only the next 10 records get computed. Okay. Okay, excellent. Hmm. So we have got, like for example, Fibonacci series. Fibonacci series need to be computed from the previously computed values, and therefore Fibonacci series cannot be parallelized the way we are planning to do that. Okay. So if you have to generate Fibonacci series, there is no easy way to distribute Fibonacci series. All right. Here are few points about testing. Okay. So always test on a small data first, and once you are in a shape where it starts running fairly good, only then you move on to big data. Because whenever you test on big data, the testing itself is going to take couple of hours, and therefore you will have smaller you will have long time running your map reduces. You will have long time spent on running map reduces instead of time given to you for fixing your code. Okay, so always run on a small data first and try to solve it then and there using a small data, and then run out on the big data. All right. Now MapReduce has got this nice quality that if it is running fairly well on smaller data, it will run proportionately on bigger data. All right. Now, also, you should test your mapper and reducer independently, and that should be part of your process. What is the suggested approach to churn data from big data in case of, okay. So suggested approach, in case you are in these situations, you need to evaluate your choice of tools first of all. Also, you need to see that what all parts of these big problems can be moved to another, can be moved to MapReduce. Okay. So say for example, full text indexing or ad hoc searching. In case of full text searching or ad hoc searching, the you might prefer the another tools such as Solar, which are available to you. Okay. In case your algorithms depend on shared global state, you might have to choose thing like Spark in this fourth point. While third point, you should see a specialized solution such as Solar, SOLR, for text indexing or searching. And in case your computation depends on previously computed step, it is actually difficult to parallelize or run it on multiple machines in any way. Okay. Now, so I was talking about testing, test on smaller data, test mapper and reducer separately. I'll show you this part. This is very important part. Now, streaming job, which we talked about, where we were having mappers and we were having reducers. And if you remember, in case of streaming jobs, Hadoop only does sorting. It doesn't do grouping for you. Okay. Therefore, it is quite simple to uh, test your script from the command line itself, right? If you see our we when I was trying to solve this problem, right? This this problem, I wrote a mapper in this form, right? Now it is quite easy to test, as I was discussing with you guys. B C, and this is my input. I pass it to I pass it to my command. Now it, right, and then I sort the output and give it to my reducer. My reducer is this one in this case. Now there you are. Good. Sounds good to you? So I just tested that instead of giving it to Hadoop, this my cmd.sh is my mapper in case of Python, in case of streaming jobs, not Python, and this is my reducer. Instead of running it through the Hadoop, all I did was I stitched it using sort command. That's all. Right. And there we are. Okay. And it gave me the results, word count immediately. Right. So testing the streaming jobs is fairly simple, and you can just whatever input file you want to have a sample, you just pipe that data to your mapper, sort the results, and give it to reducer. That's all, and you get the and save it in the output file. That's fairly straightforward. All right. Now, similar thing what we did in case of streaming job, for similar thing, if you're writing in Java, you can use MR unit, which is really simple. Okay. So we'll show you the MR unit code, and that should be good enough for you. So this is clear. Okay. Now I want to show you some more things. Rajnikant, I would strongly recommend that in case you plan to make a career in any of the server side technologies, you should learn Unix. Okay, because that makes life so much easier. And in even not even in case of Hadoop, but anywhere, if you are on the back end side, then learning Unix is a far better and better option, because it's used a lot and a lot. To your surprise, when Microsoft launched Bing, the backend was mostly in, I mean, most of their servers were Linux boxes. Okay. So because it is easy to manage the backend using Linux, and because it has the full-fledged Unix commands, and once you get the taste of Unix commands, as I was showing you that how do you do this, how do you do that, how do you do this in all in Unix commands, you will realize that it is quite powerful, and you will also start using all those commands as part of your Windows if you install Cygwin kind of environment. All right, but it's my personal suggestion for most of the people who prefer to work on the back end to go for to understand Unix part. Okay. So that is how it is, because all of most of these tools are built by the people who love Unix, and therefore most of these things are easy to handle with Unix. And some of the trainers also enjoy working with Unix, and therefore they try to demonstrate things in Unix only. All right. Now let's move on. Okay, so there is one more point I wanted to make. To test test predictions test predictions, you may want to test the past. Okay, so other part is, although it is not related to MapReduce per se, but in general, whenever you are doing a testing on big data, the testing itself is a mammoth task. It has to be done exactly the way testing of any big data solution is to be done exactly the way a development happens. You need to plan the test cases, you need to manage the data, you need to do all sorts of magic during testing, right? Let's take a case of my recommendation engine. So we built a recommendation engine on top of, say, we had a record, say 1 billion records were there, on which we had to give the recommendation. What does it mean by recommendation? We had user ID, product ID, and how much this user ID likes this particular product. That was the third column called rating. Now, based on this, we had to give the recommendation saying this user ID will like this particular product, and the chances of he liking this particular product is this much. So the input and output format was exactly same: user ID, product ID, and then rating. And as a part of recommendation, user ID, product ID, and this is the this is how much he might like it. Okay, the strength of the recommendation. Now, fine, we wrote the recommendation, it started giving great results, but how do we know that it's a great results? We are trying to predict the future, and how do we know that this oracle, when I say is the future predictor, is telling us the truth? How do we know that this person who is telling the future is telling us the truth, right? So when big data testing comes into play, you need to think about creative ways to figure out how do we do the testing such that we can determine whether these predictions are right or wrong. So what we did instead is we took half of the data, okay, and then figured out the predictions and then compared with the rest of the data. So if somebody predicted my behavior before the data of 2014, right, and they must have said that Sandeep Giri is going to like XYZ movie, or Sandeep Giri is going to like uh, some movie which was released earlier this year. And then after they have given the recommendation, I'll just compare whether I actually liked this movie or not. Okay. And if their predictions are true based on my little past, that means this recommendation engine is good. Okay. And that's what exactly we did. Do I make sense? So it's like saying that, okay, you can predict my data. So here is my ratings from 1980 till 2013. Now tell me whether I like these movies which got released this year or not, right? And that's what we do, right? Whenever there is a guy who comes to your home and says, I can predict the future, you tell him that, okay, let's take one step back. You try to predict my past. Did I do this? Did I do that? Did I do this? Did I do that? And that's what it is all about, testing the recommendations. All right, Bhupati, should I repeat once again? Great, great. Perfect. Perfect. So that is another part of testing. You need to pay a clear attention. And even if the problem looks impossible to test, such as predictions, there are ways to test it. Okay. There are ways to test it. Okay. And now I'm going to go a bit into Java. Those people who is comfortable with Java in the session. Okay. Amar knows. And okay. So probably only Amar knows Java. And okay, good, good. So Virdi also is okay. Rajnikant is okay. Okay. So this is a bit about, I'll try to explain to everybody. Unlike our Python job, where we all we did was key values were separated by a tab, and we were able to, just like any kind of standard input, standard output kind of problem, we stitched both the things together immediately. Here, you require a little bit of more programming, planning, and hence little bit of more code. Okay. So first you define something like a stub mapper. Okay, stub mapper. I mean, this is the name of the file, which you can keep any name as long as it extends a class, like class called mapper. And important part of templatization, like in C++ you have template. Similarly, we have generics in Java. We say that this mapper takes input in the form of the input is long and text, key is long and value is text, and output of this mapper is going to be key and a number. Okay, this is the declaration. Okay, okay. So we talked about how to write map reduce, right? We define key values and we do all of that. How to do exactly that using in Java, if you have to write code for doing that in Java, right? So you create a function called mapper, then you create a function called reducer, and then you stitch them together use in a function in class called driver, and then run it. It's as simple as that. Okay. So you defined a class which has the function of mapping, and you defined a class which has a function of reducing, and you stitch them together via a job, and then you run it. It's as simple as that. Okay. Now I'll show you, or should I show you a real example? I had a real example. No worries, we will take care of that part in the next session. All right, we will talk about some more things. And yeah, so let me just boot my Eclipse. Oh, okay. Actually, our my course is. So, how many of you are, keeping a close eye on the this one? As in when we finish a session, we make the content available for that session. This is for another batch. Okay, today is the third session, right? All right. So we have, yeah, yeah. So this demo of this Java code we will take care in the next one. Here all I wanted to demonstrate that it's not too difficult to write in Java. All you have to do is just have this kind of declaration. So this stuff, this whole code which we have written, the only thing you need to change is either this mapper name, whatever name you want to give, or the data type you are going to give out. Here, since we are going to give out key, and it's a word count problem, right? So we are talking about a word count problem here. So in word count, the output is string and number, therefore it's text and int writable. Similarly, for the reduce, the values are grouped together and the values are integers, right? The counts, and so on. Yes, we are inheriting from the base class. So stub mapper is basically extending the mapper which is inheriting the base class called mapper. Stub reducer is our class which is extending or inheriting from reducer, and we stitch together here by the way of creating a job and telling the job that this is your mapper class, this is your reducer class, and do the job. All right. So this is what it is. I'll give you a demo of this thing using Eclipse in the next session, which is on next weekend. Now, the assignment for this today's class, yes, in stub mapper as well as stub reducer, here your code will go. You will take the input value, you will process them and put them in the output. Okay. All right. Similar is the case here. Similar is the case with the stub reducer, and also in the stub driver you can say I want these many reducer jobs. Generally by default the reducer job is singular, which is one, but in case you want it you can configure that you want more reducer and so on. All right, and this is my file which you want to process, that is configured and specified in stub driver. Okay. And also the streaming job which we talked about is written exactly internally, it is written like this. Okay. Now, as an assignment for today, make sure that you finish all these problems in your own favorite language. If you are not hands on with any programming language, feel free to write in a natural language. Any syntax is okay with me, but make sure that you write down the MapReduce code in your own favorite language. Okay, even if it's French, I'm okay with that. Okay, so Rajnikant will give you a demonstration of doing Eclipse with the Hadoop, right, in the next session. Don't worry. All right. So all of you, please make sure that you, even if you're stuck, because you will not realize that you are stuck unless you start writing in your favorite language. Okay, once you start writing, then you will realize, oh, he was right, that I did not understand this part, I do not. Then please drop me an email saying this is where I'm stuck. Okay, so that I can assist you, and this is the best time. You have got 1 week to solve all of this and finish the assignment, and it is not more than couple of hours task. Okay, so write code in MR, write code of all those four problems. I mean, those are five problems actually: one, two, three A, three B, and four. So solve those things. Make sure you drop me an email because your certificate will depend on this assignment. All right. So at the end of the session, we go through all the assignments which we have given and how did you perform, and based on that, we will be grading your certificate. And no cheating, please. Right. If you are stuck, drop me an email. Drop me an email, and then okay. So another assignment for today's class. This is little difficult and little theoretical. All of you these days must have been using smartphones, right? And when you type a word while writing a message to somebody on WhatsApp, the phone gives you a recommendation of a word, right? Now, how does it give that recommendation of a word? As you finish writing one word and click space bar, it automatically gives the recommendation of the next word you can type. If you write happy, it gives birthday as the recommendation. If you write hello, if you write how, HOW, it automatically gives you the recommendations like are, do, that kind of thing, thinking that you might be writing how are you, how do you do, right? Now, yes, yes. Now, if you are given the Wikipedia text, how will you build such recommendations? You are given whole Wikipedia, okay, which is few GBs. The Wikipedia's text is few GBs. If you are given a whole Wikipedia text, how would you form these recommendations? That is the assignment. All right. And then in the next session, we are going to discuss in detail the pitfalls of the approaches which we will take. Okay. So that we can make a formation ground for other things which we are going to discuss in the next assignment. Okay. We'll discuss why our general approaches are bad and in this problem. Okay. But make sure you attempt all the problems we have discussed so far. This is session number 3, and there will be 8 more sessions, such sessions. So, and there will be assignments for each session. So make sure you make a habit of finishing assignment. Otherwise, there will be too much of things at the end of session. Okay. So please make sure that you finish all the assignments. All right. Devote a time every day and work with us, and that will actually help you a lot. Okay. So to submit an assignment, just create a new fresh Google Doc, and with the problems, just duplicate the problems document as a new Google Doc and then share the doc with me. All right. The benefit of creating a Google Doc is that I can line by line put the comments in your question, and then that makes the life easier. You immediately get a feedback that I have responded. All right. So that's pretty much for today. And let's meet tomorrow, I mean next weekend, next Saturday. And please work with me instead of just listening and then forgetting. Please work with me so that I can so that in case you get stuck, I help you out. All right. Now, those of you, because Regular expression is such an important thing. If you noticed in SED command, we use regular expressions everywhere, right? We did a SED this, SED that. So regular expressions will be used and used in most of the programming. In case, so how many of you do not know about regular expressions? Amar, Bhupati, Rajnikant, Sai, Sini, Virdi. Okay, okay. I'm talking about regular expressions, Amar. So regular expressions are in regex. I'm talking about this kind of regular expressions. Where did it go? Okay. So when we wrote mycmd.sh, there were regular expressions everywhere. Do you see the regular expression here? Substitute this with the new line. This is new line. And here you see this regular expression. So these are regular expressions. So those who do not know, let me know so that we can have a session planned. I'm planning to have a session maybe during a weekday on regex. There are other people from other classes also, and future past classes also who want to attend the regular expression session. Okay, okay. So Virdi wants it. Not Amar. Regular expression is like wildcard characters. You remember in those in DOS we have dir star.txt or dir star.star. That star.star is a wildcard character. Similar to that is a very extended form. Whenever you have to do text search, text replacement, you use or text validation, you need to use the regular expression like this one. Do you see? Here, this is a regular expression which says any character from A to Z, capital A to Z, and 0 to 9. All right. So this is quite helpful in terms of. Okay, Sini would like to have, Amar would have, Sai would have. Okay, okay, okay. So a weekday class on the evening or in the sometime will be okay, right? Because this class is going to be like 1 hour class, 1 hour class. So okay, great, great. So I'll plan it accordingly. It is going to be just 1 hour class and really fast-paced class, and we'll share that with you. All right, let you know. Great, great. So this is sort of a complimentary class because what I realized was lots of people in our sessions. I assumed that people knew about regex, and when some people asked a lot of questions, then I realized that my assumption was wrong, and therefore we kept a separate session. So important lesson to me and to you is that you should be asking a lot of questions, even in the class, after the class, before the class. Drop an email. In case you are really stuck with something, give me a call and we will solve your problem. And that will help me understand that there is some, if there is something wrong anywhere in the session, we'll fix it immediately. All right. So thank you very much. See you next week and bye bye. Great. Amar, actually everything is going to be available in your sessions. If you go, I'll show you. Can you see the screen, Amar? So in the October 18th sessions, if you see, session 2 has been uploaded and the recording is available over here. You can just play here. And Now, the session 3 will be available here, not yet uploaded. It will be available. Oh, you want to download the video? I don't know if YouTube allows you to download. So, okay, I need to check if I can set up such that we can download. Okay, okay, let me see if we can make it downloadable. All right. Otherwise, yeah, we'll find out other ways to upload and download it. All right. So, yeah, thank you for making that note. Great. See you then. Have a nice time. Or you can, yeah, you can, Amar, you could also use in the meantime called keep feed if I'm not able to do it, because this YouTube may not be allowing me to upload. Yeah. Thank you, Virdi, for that. Is it so? Okay, okay. Let me try. Okay. All right. Thank you very much and have a good day. Bye bye. Bye, Virdi. Bye, Amar. Bye, Bhupati. Bye, Rajnikant. Bye, Srini. Bye, Amar. All right. Bye bye. Have a good day.